Alright, so let's go ahead and let's get rolling with this. This is a pretty simple section. Today we're going to talk about the Pythagorean Theorem. I know you would have learned about it last year, and Algebra 1 spent maybe one day on it, and probably at some point in time in middle school you probably talked about it as well. So we're going to do pretty much the same thing, maybe add a couple of things to it. Pythagorean Theorem, first and foremost, deals with right triangles, so a triangle that have a right angle. Now, in a right triangle, the sides of the triangle have different names. So the longest side, oftentimes we're going to call it C, but specifically we call it the hypotenuse. So it's going to be the side across from the right angle. The other two sides can be interchanged. You could call either one of them A or B. They're called the legs, so the actual sides that make up the right angle. So what the Pythagorean Theorem tells you, it says, super wordy definition here, if a triangle is a right triangle, then the sum of the squares of the lengths of the legs is equal to the square of the length of the hypotenuse. It just means A squared plus B squared equals C squared, which you should be familiar with. And the converse of the Pythagorean Theorem just pretty much says the opposite. If in a triangle A squared plus B squared equals C squared, like if the sides work out in the Pythagorean Theorem, then it would have to be a right triangle. So that kind of sums up what we're doing today. So one of the things we're going to do today is we're going to be finding the length of a hypotenuse, or maybe we're going to be finding the length of a leg. Another thing we're going to be doing today on the right-hand side, we're not going to do it in this example, but we're going to talk about things that are called a Pythagorean triple. A Pythagorean triple is a set of three numbers. They just work in the Pythagorean Theorem. So for example, 3, 4, and 5. If you had a triangle with lengths 3, 4, and 5, it would be a right triangle because 3 squared plus 4 squared equals 5 squared. Okay? And interesting things about Pythagorean triples, all factors of the Pythagorean triples also work, which is kind of interesting. But it's just basically sets of numbers that work in the Pythagorean Theorem. So let's use the Pythagorean Theorem to find lengths of the hypotenuse. So how you know you're looking for the hypotenuse? This side, AB right here, the longest side, the side across from the right angle, that's your C. That's your hypotenuse. So to find the hypotenuse, you're going to take A squared plus B squared, set it equal to C squared. Now, what I mentioned is that A and B can be interchanged. If you want to say 20 is A and 21 is B, great. If you want to say 21 is A and 20 is B, great. It doesn't matter. So if we do 20 squared plus 21 squared, it should equal C squared, which is what I'm looking for. Now, the Pythagorean Theorem is really simple, but there are some really common mistakes that students make. You have to square these first. You have to take 20 squared, which is 400. You have to take 21 squared, which is 441, and set that equal to C squared. And keep in mind that the whole point here, I'm trying to solve for C, not C squared. But before I can do that, I need to actually add these together. I need to take 400 plus 441, and I would get 841 equals C squared. Now, once again, I don't want to solve for C squared. I want to solve for C. So, to get rid of a squared, the opposite of squaring something, square root is the square root. So, you're going to square both sides. Now, today you're going to want to write your answers in simplest radical form. So, before you start racking your brains for perfect square factors of 841, the first thing I would suggest you do in your calculator, just do the square root of 841. Maybe it's a perfect square, because we're not super familiar with perfect squares past like 144 and on from there. So if you do take the square root of 841, you get 29. 29, perfect. So that missing side would be 29. Now you can use the Pythagorean Theorem not just to find the hypotenuse, but if you are missing a leg. So like in this one, notice I have C, my C is 20, and I have one of the legs, but I'm missing one of the legs. So I'm missing either my A or B. So you're going to do the same thing here. You're going to take the legs, x and 8. You're going to square them and add them. So you're going to take x squared plus 8 squared. And you're going to set set it equal to c squared, except this time I know what c is. It's 20, so we're going to set it equal to 20 squared. And kind of like the last one, you want to go ahead and actually square these numbers. So we're going to do x squared plus 64 equals 20 squared is 400. Now, if we're going to solve for x, I first need to solve for x squared. So just like if this were a one-step equation, we're going to subtract 64 from both sides. And we have x squared equals 336. And just like the last one, to get rid of the squared, we're going to square root it. Now, like I said, the first thing I would recommend you do, plug this in your calculator and see if this is a perfect square factor. In this case, it's not. How you're going to know it's not a perfect square factor, it's going to end up being a decimal. Okay, I don't want decimal answers. I want simplest radical form. So this is where you either need to start looking for perfect square factors of 336 or do the cake method. Okay? For numbers like this, where we're not a little bit bigger and maybe not super familiar with the factors, I might personally turn to the cake method. If you like a perfect square factor method, go for it. If you like doing a factor tree, that's the same thing as the cake method, just looks different. So, for those who like the cake method, if we were to build our cake of 336, I would probably start by dividing out of 3, and I'd get 112. I would probably divide out of 2, and I'd get 56. A 2, I'd get 28. A 2, I'd get 14. A 2, I'd get 7. And a 7, I'd get 1. So I have a pair of 2s and another pair of 2s. Remember what happens with these? This is a 2 times 2 under the radical, which is 2 times 2 is 4, but the square root of 4 is 2. So a pair of 2s becomes 1, 2 on the outside. This pair of 2s becomes 1, 2 on the outside. So 2 times 2 is 4. Now, still underneath the radical is the 3 times 7. I can't take the square root of 3. I can't take the square root of 7. So we're just going to multiply those together, and it would be 4 square root of 21. If you're looking for perfect square factors, if you're just like dividing by 4, divide by 9, divide by, until you find what it would be 16. It would be 16 times 21 is what you would end up with. Take the square root of each one of those and you would get the same answer. Okay? And I think the problems today are a little bit easier radicals to simplify. So, okay, now the other thing we're going to do today, the other two theorems don't actually deal with right triangles. They do, in a way, deal with the Pythagorean theorem, an application of the Pythagorean theorem, but they are not dealing with right triangles. They are dealing with triangles that are not right triangles. So if you have a triangle that's not a right triangle, it is either an obtuse triangle or an acute triangle. So an obtuse triangle is going to have one obtuse angle. So an angle greater than 90 degrees. And the other two would be acute angles. An acute triangle is going to have all 3 acute angles. So all angles are less than 90. Okay? Now it turns out that by using an application of the Pythagorean theorem, you can decide whether a triangle is going to be a right triangle, obviously, because if it works in a squared plus b squared equals c squared, it's a right triangle. But it turns out that if you plug those numbers in, you can tell if it's not a right triangle, whether it's going to be acute or obtuse. And how you're going to know is you're going to look at the longest side. So out of your 3 side lengths, you're going to look at the longest side. Okay? You're going to square it, and you're going to compare that number to the sum of the squares of the other 2. Okay, so the longest side, you're going to square it. You're going to take the other 2 sides and do just like you do with the Pythagorean theorem. You're going to square them and add them. When you compare those 2 numbers, if the square of the longest side is greater than the sum of the squares of the other 2, it's obtuse. And if it's less than, then it's acute. That's what these 2 theorems tell me. So if we look at this triangle example right here, I have a triangle that has side lengths 6, 11, and 14. If I want to know if it is acute, obtuse, or right, the first thing I need to do is I need to pick out the longest side, which in a problem like this is pretty easy to do. The longest side here would be 14, right? So what we're going to do is we're going to square that. We're going to take 14 squared, and we would get 196. Now, you're going to take the other sides. You're going to take the sum of the squares. So with the 6 and the 11, you're going to do 6 squared plus 11 squared, just like you do with the Pythagorean theorem. 6 squared is 36, 11 squared is 121. When I add those together, I get 157. Now you're going to compare these two numbers. In this case, 196 is greater than 157. So if the square of that longest side is bigger than the sum of the squares of the other one, this is going to be an obtuse triangle. If it was the opposite way, it would be an acute triangle. Okay, questions on any of that? Yes?
If they were even, would it be right?
It would be, yes. Good application. Okay, all right, so we need to set up our table of contents. Your next open page should be page 17. So if you have not set up your table of contents yet, that should be on page 17, which means your vocab should be on page 18. So on page 19, this is going to be section 8.1, the Pythagorean theorem and its converse. So I would say for the most part what we do today is really pretty simple. Most of it is the same thing you would have done last year, and a lot of it's what you would have done in middle school. So the first thing, want to find the value of x, just like we did over on the left-hand side. So, and on all of these, whether it says so or not in the directions, we want to write our answer in simplest radical form. Okay, so number 1, let's draw our nice little right triangle. The legs are going to be 7 and 9. The hypotenuse is going to be x. So the Pythagorean theorem is pretty simple to use, but you do have to make sure you identify whether you're given the hypotenuse, if you're looking for the hypotenuse. In this case, I'm looking for c, right? I'm looking for that x. So you're going to take the sum of the squares of the legs. We're going to take 7 squared plus 9 squared. That's going to equal x squared. If you want to put c squared, whatever, no problem there. Okay, remember, you have to actually square these. You have to take 9 squared, which is 49. You have to take 9 squared, which is 81. So 49 plus 81 equals x squared. And you have to actually add those together. 49 plus 81 gives me 130 equals x squared. Remember, I'm trying to solve for x, not x squared. So just like the other ones, to get rid of the square, we would square root both sides. Like I said, what I would probably start with doing, see if you can take the square root of 30. It's going to give you a decimal, so it's not going to work. So what I need to do is I need to write this in simplest radical form. Okay, so me personally, if I see perfect square factors, I will usually go the perfect square factor route. Or if I see like big factors that I know I can break down easily, I might do that. And then if it's like a huge number, I may just go for the cake method. So for this one, what I see is I'm like, okay, well that's 13 times 10. That's an easy way to break that down. I can't take the square root of either one of those, but with 10, I can do 2 times 5. I can do the square root of either one of those, and that's the most I can break that down. Right? This would be the prime factorization, 13, 2, and 5. None of those are perfect squares, which means this has no perfect square factors, which means you just leave it as the square root of 130. It's like if you end up with a fraction, 7 over 15, and you tried to reduce it, 7 and 15 don't have any common factors, you just leave it as 7 over 15. You would just leave it as the square root of 130. Okay, number 2, let's try another right triangle. Okay, this time the hypotenuse is going to be 10. One of the legs is going to be 5, and the other legs is going to be x. Now, what's nice about the Pythagorean theorem is it's the same formula. You're just going to plug the numbers in different places. Because this time, like we did on the left-hand side, I have the c. It's going to equal 10 squared. What I don't have is one of the legs. So you're going to square the legs and add them together. So you're going to take x squared plus 5 squared, and you're going to, x squared, 5 squared, and you're going to set it equal to the hypotenuse squared, so 10 squared. Okay, so it's going to be x squared plus 25 equals 100. And this is just like a simple one-step equation. Move your 25, so x squared equals 75. And then just like the other ones, to get rid of this squared, we square root them. Can't take the square root of 75, but there's a super easy perfect square factor of 75. 25, right? 25 times 3. Keep in mind when you do this, they're still under the radical sign. So you can take the square root of 25, it's 5, but you can't take the square root of 3, it just stays the square root of 3. Questions on 1 or 2? Okay, now these ones, we're going to be looking at a set of number. We're going to decide if they are a Pythagorean triple. A Pythagorean triple just means, could they be 3 sides of a right triangle? That's it. So, number 3, let's say we have, number 3. Okay, number 7, 24, and 25. Now, if this is a Pythagorean triple, it means I can take a squared, so 7 squared, plus b squared, which is 24 squared, and it would equal 25 squared. Well, 49 is 7 squared. 24 squared is 576. 25 squared is 625. And then if I take 49 plus 576, guess what I get? 645. So since they equal, since I can take a squared plus b squared equals c squared, yes, these are called a Pythagorean triple. If you had 3 side lengths of a triangle that were 7, 24, and 25, it would be a right triangle. Okay, number 4, if I have 8, 15, and 16. So, same idea. If this is the Pythagorean triple, I should be able to take 8 squared plus 15 squared, and it should equal 16 squared. So 8 squared is 64, 15 squared is 225, 16 squared is 256, but 64 plus 225 gives me 289. Right, they're not equal. Close, but it doesn't matter. They're not equal, which means this would not be a right triangle. This is either obtuse or acute, which is actually what we're going to do next. Questions on those ones? Okay, last thing. The lengths of a triangle are given. We want to classify it as acute, right, or obtuse. So we're doing basically the same thing, kind of in the opposite order, because what you're looking at is you're looking at the square of the longest side compared to the sum of the squares of the other 2 sides. So I know oftentimes you kind of have it switched, so we'll try to keep it in that order there. All right, so let's do number 5. Okay, number 5, if I have a triangle that's 11, 12, and 15. Okay, so what we're going to do is we're going to take the longest side first. So which is the longest side? 15. We're going to square it. So 15 squared is 225. Then we're going to take the other 2 sides, square them, and add them. So we're going to take 11 squared plus 12 squared. So 121 plus 144 gives me 265. So 225 greater than or less than 265? Less than. So since the longest side is small, since the square of the longest side is smaller than the sum of the squares of the other 2, this is acute. Now, pretty simple. The only way that these get a little trickier, as It's going to sound silly, but deciding which is your longest side. So for example, if I have something that says the square root of 11, the square root of 13, and 5. Okay, well I need to figure out which of those is the longest side, which is kind of hard to do. I mean, right? I know the square root of 13 would have to be bigger than the square root of 11 because 13 is greater than 11, but I'm not really sure how to compare those to 5. How can I compare all those? That'd be one way to do it. If I wanted to think about inverses or opposites, and if I wanted to put this under a radical sign, you would say 5 is the same thing as the square root of 25. That's one way you could do it. 25 is the biggest. Another way, you have another idea?
Guess the other ones, but like, what's that called?
I think you're on the right track. If you put the square root of 11 in your calculator, it's going to give you a decimal. It's going to give you like 3.3, I think.
Yeah.
And the square root of 13 gives you like 3.6. I can compare 3.3, 3.6, and 5, right? So two ways you could think about that. Either way, 5 is the biggest. So we're going to take 5 squared, which is 25. Now the other two, we're going to square them and add them. So we're going to take the square root of 11 squared plus the square root of 13 squared. What happens when you take the square root of 11 squared? They cancel out, just like it did above, right? If I want to get rid of a squared, I square root it. But guess what? If I want to get rid of a square root, you just square it. So this gives you 11. This gives you 13, which gives you 24. And 25 is bigger than 24, which means what kind of triangle is this? Obtuse. Very good.